So the next topic here is transformation equations. So the transformation equations for coordinate of a point. So that means we have here two coordinate, you can say, systems like this. This is basically x1, this is x2, and this is x3, and we have some another coordinate system. So I can say that this is some, you can say that this is some x1 dash, this is x2 dash, and this is some, you can say that x3 dash. So this is the k system, and this is the dotted portion represent the k dash system. So this is the coordinate, you can say, planes here, and they have same origin, and the unit vector is along the same, like here the unit vector is e1 dash, here the unit vector is e2 dash, and here the unit vector is e3 dash, and here is e1 dash, e2 dash, and e3 dash. So this is the unit vector e1, e2, and e3, and these are the unit vector e1 dash, e2 dash, and e3 dash. So these are the two coordinate system k and k dash. So here I am taking some point in these two coordinate system, like this is the position vector from P, and this is the basically x1, x2, x3, and x1 dash, x2 dash, and x3 dash. So this is the, you can say, the coordinate we are taking here. So these are the two rectangular coordinate system k and k dash, and they have the same origin at O. Now first we are going to find the transformation equation, that expressing the coordinates, I can say that x1 dash, x2 dash, and x3 dash of some arbitrary point in the k dash system in the terms of the x1, x2, and x3 in the k system, and just like that I found the value of another system, vice versa. Now here is, we have to take the condition that we have to let r and r dash, the position vector of any point P in K and K dash system, that we have that condition that this unit vector is equals to this, like these two position vectors are equal here. So that means I can write it as, the equation for this is x1 dash e1 dash plus x2 dash e2 dash plus x3 dash e3 dash. Like if I have generally r as some position vector, so I can write it as x1 yj plus zk, like that. So in this system we have unit vector here is e1, e2, and e3, and here xyz, in place of xyz I have x1, x2, and x3. So I can write it like this. This is equals to x1 e1 plus x2 e2 plus x3 e3. So we have this result. So that means generally I can write it as xj dash ej dash, that is equals to xi ei, where I and j are equals to 1, 2, and 3. So generally I can write it in summation convection form like this. Now further is for the component, I can say that for component xj dash, we are taking the dot product with this, you can say, or with this journal equation 1. Then we have xj dash with this term, I can say that we have this vector, that is ej dash into ej dash, like this xi dot product with equation 1 with, you can say that for the component xi, taking the dot product of equation this one with ej dash. So I'm taking the dot product of ej dash with this equation 1. So I have xj dash ej into ej, that is equals to xi I into ei dot ej dash. So in the next step I can write this term like ej dash into ei into xi, And we discussed earlier that this is basically the definition of direction cosines of jth axis of the k dash system. So I can write it as x j dash, that is equals to, you can say that l j I xi. So these are basically this l j I are the direction cosines of the, you can say, jth axis of the k dash system with the, and its, you can say, its product with the ith axis of the, you can say, of the k system. So this equation, you can say, this is the equation 2. This equation 2 is called the equation of transformation for the coordinates of point P from the system K to the system K dash. So this is basically the equation from system K to the system K dash. This is the transformation of coordinates of the point P from the system K to the system K dash. Now next is we are going to find some another expression, or I can write it, I can write it further in the equations form. Like I'm making the equation of this, that is x1 dash, that is equals to l11 x1 plus l12 x2 plus l13 x3, and further is x2 dash, that is equals to l21 x1 plus l22 x2 plus l23 x3, and further is x3 dash, that is equals to l31 x1 plus l32 x2 plus l33 x3. So these are the general equation. I am expanding this term like this in the term of 1, 2 and 3. Now further in the next step I can write it, I am going to write it in the matrix form. So in the matrix form I can write it as, we have x1 dash, x2 dash and x3 dash. This result is equals to l11 l12 l13 l21 l22 l23 l31 l32 l33, and this as a whole multiplied with x1 x2 and x3. So that means I am writing these equation in the form of the matrices like in the form of the matrix like this. So this is called the transformation matrix of that equation. Now further is we have the inverse transformation law. Inverse, you can say that inverse transformation law. So the previous one is basically a transformation law. Now I'm going to find the inverse transformation law. That means I am going to find this transformation for the coordinates of the point P from the system now from K dash through the system K. So the equation for this is, generally I can write it as xi, that is equals to lji and xj dash. So I am going to, you can say, this is the equation of transformation, and here I am going to make it opposite. So here is simple xi and here is xj dash, but here xj dash is equals to lji and xi. So now I am going to write this in the in this form. So for this I can say that this is basically how this result is equals to xi. I am going to prove it, that since I know that lji xj dash, that is equals to lji, and I can write it, this is the basically the definition of the direction cosine. So I can write it as this is basically the transformation law. So the value of xj is basically ljixi, so I am writing here like ljk and xk using the transformation law. So I have this result and I am writing here like lji ljk xk. So as we know that this is same, so that means I can write it in the form of the Kronecker delta, that delta ik, because j is common here, ik xk, and this is same here, so that means this result is equals to xi. We proved the result in previous lectures that del of I k xk is equals to xi. So this is the proof of this result. Now this is called the equation 3. Now I'm going to take the dot product of equation, you can say that 1 with the equation 3 with the, you can say that ei unit vector. I'm taking the dot product of this equation 1, you can say here, with the ei. Here I take the dot product with ej dash, but here I am going to take the dot product of this equation with ei. So the equation becomes xj, that is xj dash ej dash ei, that is equals to xi ei dot ei. So this is the result here, and this result is basically equals to xi, the dot product of the same unit vector is 1, so this result is xi. And if we take the definition, using the definition we can say that this result is basically equals to lij and into, you can say that xj dash. So this is the equation here. So the equation 3 can, you can say, equivalently be written as that xj is equals to lij xi dash, like this. Like I write this term in this. I'm changing the indices here, so that doesn't matter. This is basically the inverse transformation law. Now further is, I'm going to express this in the equation form, like x1, that is equals to l11 x1 dash plus l21 x2 dash plus l31 x3 dash. Now further is taking l2, so that is l12 x1 dash plus l22 x2 dash plus l. Now here is 3, but the changes in the j-axis, so l32 is x3 dash, and x3, that is equals to l13 x1 dash plus l23 x2 dash plus l33 x3 dash. So these are the equations here. Now I am going to write these equation in the form of the matrix. So that means this is written as x1 x2 x3, and that result is equals to l11 l21 l31 l12 l22 l32 l13 l23 l33 into, we have x1 dash x2 dash and x3 dash. So if you solve this matrix, we got these equations. So this is basically the transformation of the equation, or the transformation law. Now next is, we have some transformation equation for the unit vector.